Hello students, in this video we'll prove the Rodrigues formula for the Laguerre polynomials and the application it gives us to the orthogonality of the Laguerre polynomials. So let's recall that the Laguerre differential equation has the form x, y, double prime plus 1 minus x, y prime plus n, y equals 0. And the method of Frobenius in a previous video gave a solution Ln of x as the sum k goes from 0 up to n, negative 1 to the k, n factorial over k factorial squared, n minus k factorial, x to the power k, as solutions, as polynomial solutions. The other solution will involve a logarithm. We'll see that in a further video, polynomial solutions. Okay? And so what I'd like to show now is the following. So we can sort of see a binomial coefficient popping up over here, right? And so now we can prove this result. It's called the Rodrigues formula. So here's the theorem due to Rodrigues. And it says that if I look at e to the x over n factorial, and then I do n derivatives of e to the negative x, e to the negative x, x to the n, that this will exactly be Ln of x. Okay? In other words, I write this polynomial as n derivatives of a product of two functions times an exponential function. This is actually an extremely useful formula in terms of I have semi-group properties here I can employ to help me figure out properties of Laplace transform and orthogonality. All right, excellent. So let's prove this. Okay, so let's recall the following. So recall a little proposition over here. The proposition is that if I do, excuse me, if I do L derivatives of f times g, that's the sum. J goes from 0 to L. L to choose J. J derivatives of f, and then L minus J derivatives of g. Okay, that's just the generalized Leibniz rule. Okay, so let's do that. So I'm going to apply Leibniz. So e to the x over n factorial dn e to the negative x, x to the n is going to be e to the x over n factorial. The sum, k, goes from 0 up to n. And I'm going to do k derivatives of e to the negative x. K derivatives of e to the negative x is negative 1 to the k, e to the negative x. That's easy to do. And then to do n minus k derivatives, so n minus k derivatives over here of x to the power of n. Okay? So now we have to figure out this formula for this thing over here. So let's think about this more abstractly and look at another sort of proposition over here to figure that out, right? So if I did L derivatives, so if I have L derivatives, dl of x to the power k, what's that going to look like? That's going to look like, maybe we should say dl and then x to the power dl, and then let's put an m over here to make sure we can use different letters over here. So m. And so what would that be? So I'm going to have, if I do one derivative, I have an m. If I do two derivatives, I'm going to have an m minus 1 come out, all the way down to m minus l plus 1, x to the what? M minus L, right? So that's the formula we get. And how does that simplify? That's really m factorial. So this thing over here is really m factorial over what? Over m minus L factorial minus L factorial x to the m minus L. So now we apply that to this situation over here, to our situation. So what's playing the role of our L? So L is being played by n minus k, and then m is being played by n, right? So what will this formula over here give us? This formula over here is going to give us m factorial, so it's going to be an n factorial over what? Over n minus, so m is going to be equal to n minus l, so it's going to be a k factorial, x to the n minus k, like that, okay? And so, of course, I have an n choose k over here as well. So then I have this thing, and I also have an n choose k, n choose k, like that. I can't forget that. All right, good. So now let's fill this in. This is going to be e to the x over n factorial. The sum, k goes from 0 up to n. And then we have a negative 1 to the k, an e to the negative x. And then I'm going to have this term over here we found out to be n factorial over k factorial, right? And then what do we have? Then we have n choose k, and n choose k is n factorial over n minus k factorial. And so what's going to happen? I have two n factorials on top, one on the bottom. That's going to cancel. That's going to cancel. And then 2k factorial, and then the e to the x's are going to cancel out as well. And so this becomes what? So this becomes just the sum. K goes from 0 up to n, negative 1 to the k, x n factorial, x to the k, over k factorial squared, n minus k factorial. And that's exactly equal to ln of x. So we just proved the Rodrigues formula. Beautiful, okay? It just comes from these general Leibniz rules and this rule for differentiating a polynomial a certain number of times. Excellent, so that's the proof of Rodrigues. And the immediate consequence of this is the following. So here's a proposition, it's an orthogonality. Okay? And the orthogonality is that if n is not equal to m, then if I integrate from 0 to infinity, ln of x, lm of x times e to the negative x dx, we get 0. And how do you prove this? Well, the proof goes as follows. So proof, let's assume that m is less than n, right? Then lm is a polynomial of degree less than, then lm is a polynomial of degree m. From the degree of lm is equal to m. And so what can I do? I can use Rodrigues to write what? This integral over here, I can simply replace this ln with the Rodrigues formula. So this integral over here becomes the integral from 0 to infinity. I have an e to the x, e to the negative x, those are going to cancel out. 1 over n factorial. And then I'll have a what? Then I'm going to have a dn of n derivatives over here of e to the negative x, e to the negative x, and then x to the n. And then I have an lm, right? And so lm of x dx. Okay, great. And so now here's a beautiful thing over here. So what's going to happen is I can integrate by parts, right? So every time I integrate by parts, I take a derivative over here and put a derivative over here. That's the foundation of integration by parts. And now since n is bigger than m over here, when I plug in x equals 0 to this expression inside the derivative, I'm going to get a 0 by virtue of the fact that there's an x over here. When I plug in infinity over here, I have an e to the negative infinity. That's going to give me 0, and that's going to infinity that's going to 0 much faster than that's going to infinity. So the boundary terms are always 0. So if I integrate by parts n minus m times, if I integrate m minus n plus 1 times, we're going to see that this is going to give me equal to 0. So this is equal to 0 after I do what? After m plus 1, which is at least bigger than or equal to m, which is permissible. I can do that, at least that many steps. Integration by parts. Okay. Well, let's stop and think about that, right? Since n is going to be at least m plus 1 by this inequality over here, right? And if I do m plus 1 derivatives of a polynomial of degree m, the polynomial of degree m cannot sustain m plus 1 derivatives. So m plus 1 derivatives of a polynomial of degree n is going to be equal to 0, right? So in other words, I've proven that these Laguerre polynomials are orthogonal with respect to the way e to the negative x dx. And that's a very, very important class of functions which pops up a lot in mathematical physics, in particular with respect to a lot of problems in quantum mechanics. So we're going to encounter this when we start to examine boundary value problems that involve certain Schrodinger equations, and we'll see that these Laguerre polynomials occur in a very natural context. Thank you very much.